Preparing for ADAS engineering at KPIT interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you design a high-level architecture for an ADAS system? I would structure the system into sensing, perception, fusion, decision-making, control, and actuation layers. Cameras, radar, and lidar provide inputs. Perception detects objects and lanes. Fusion improves confidence. Planning selects actions. Control generates steering or braking commands. I would add health monitoring, timestamps, cybersecurity, and fail-safe behavior across every layer. The architecture must respect latency, compute, and ISO 26262 constraints, while keeping interfaces modular for different vehicle programs and sensor configurations. While answering, cover sensor inputs, perception, sensor fusion, localization, planning, control, actuation, diagnostics, real-time constraints, functional safety, and communication through automotive networks such as CAN or Ethernet. Question 2. What are the main challenges in fusing camera, radar, and lidar data? The core challenge is combining measurements that differ in timing, coordinate frames, accuracy, and failure modes. I would calibrate extrinsic and intrinsic parameters, synchronize timestamps, transform detections into a common frame, and associate observations using spatial and temporal gates. Radar supplies velocity and robustness, cameras provide semantics, and lidar offers geometry. A probabilistic fusion method should preserve uncertainty and degrade gracefully when one sensor becomes unavailable or unreliable. Make sure to cover coordinate transformations, time synchronization, sensor calibration, differing resolutions and detection characteristics, association algorithms, uncertainty modeling, redundant observations, and handling missing or contradictory measurements. Question 3. How would you calibrate a forward-facing ADAS camera? I would first estimate intrinsic parameters, including focal length, principal point, and distortion, using calibrated targets. Then I would determine the camera's extrinsic rotation and translation relative to the vehicle coordinate system. I would validate both through reprojection error in road geometry, such as lane alignment and horizon position. Production systems also need end-of-line procedures, mounting tolerance checks, diagnostic thresholds, and recalibration detection because vibration, repairs, or temperature can shift alignment. In your answer, talk about intrinsic and extrinsic calibration, lens distortion, camera-to-vehicle transformation, checkerboards or road targets, reprojection error, online validation, environmental effects, and calibration quality thresholds. Question 4. How would you develop a lane detection algorithm for highway driving? I would combine a learned segmentation model with geometric and temporal reasoning. After image normalization, I would transform the road into a bird's eye view, segment lane markings, fit smooth curves, and track them across frames. The system should estimate lane confidence, width, curvature, and vehicle offset rather than returning pixels alone. I would test faded markings, shadows, construction zones, and merges, then fall back to a reduced function mode when confidence drops. Be sure to mention image preprocessing, perspective transformation, semantic segmentation or feature extraction, polynomial lane fitting, temporal tracking, confidence estimation, curved and partially occluded lanes, and fallback behavior. Question 5. Which metrics would you use to evaluate an object detection model for ADAS? I would use precision, recall, F1, and map with IOU thresholds, but those alone are insufficient for safety. I would separately measure missed pedestrians, vehicles, cyclists, and motorcycles by distance, lighting, weather, and relative speed. Latency, throughput, confidence calibration, and temporal stability also matter. For ADAS, I would prioritize safety-relevant false negatives, define scenario-based acceptance criteria, and examine error distributions instead of relying on one aggregate score. Focus on precision, recall, F1 score, mean average precision, intersection over union, distance-dependent performance, false negatives, false positives, latency, confidence calibration, and safety-critical scenario coverage. Question 6. When would you choose radar over camera or lidar for an ADAS function? Radar is especially valuable when direct velocity measurement and weather robustness are important. It performs well for adaptive cruise control, blind spot monitoring, and target ranging in rain or darkness. Cameras provide richer semantic information at lower cost, while lidar supplies detailed three-dimensional geometry but usually increases cost and packaging complexity. I would not select one universally. I would match sensor characteristics to the function and use complementary sensing where safety demands redundancy. In your answer, compare range, velocity measurement, semantics, resolution, cost, weather robustness, environmental limitations, processing requirements, and how each sensor supports functions such as ACC, AEB, and blind spot detection. Question 7. Explain how a Kalman filter can track vehicles detected by radar. I would represent a target with position and velocity, then predict its next state using a motion model and process noise covariance. When radar provides a measurement, the filter computes the innovation, weights it using measurement uncertainty, and corrects the estimate and covariance. A standard Kalman filter suits linear models. EKF handles nonlinear transformations. Practical tracking also requires association gates, track confirmation, timeout rules, and careful tuning for maneuvers. Cover the state vector, motion model, prediction and correction steps, process and measurement noise, covariance, data association, nonlinear variants such as EKF or UKF, and track initialization and deletion. Question 8. How would you implement adaptive cruise control using radar data? I would select the relevant lead vehicle using lane association, range, and relative velocity, then compute a desired distance from vehicle speed and a configurable time gap. A longitudinal controller, often PID or model predictive control, would regulate the spacing while limiting acceleration and jerk for comfort. I would handle cut-ins, stopped objects, sensor dropouts, and driver braking explicitly. If confidence or system health falls below threshold, the feature should disengage predictably. Make sure to cover target selection, relative distance and velocity, desired time gap, longitudinal control, acceleration and jerk limits, cut-in handling, sensor confidence, driver override, and safe fallback behavior. Question 9. What makes automatic emergency braking more difficult than ordinary object detection? AEB must decide not merely whether an object exists, but whether collision is imminent and braking is necessary. I would estimate relative motion, time to collision, ego braking capability, object type, and predicted trajectories while accounting for perception and actuator latency. Thresholds must balance early intervention against nuisance braking. The design needs confidence checks, driver override handling, degraded modes, and extensive validation across speeds, road surfaces, occlusions, and vulnerable road users. Discuss time to collision, object classification, trajectory prediction, braking distance, reaction latency, road context, false activations, pedestrian behavior, actuation coordination, and safety validation under varied speeds and conditions. Question 10. How does ISO 26262 influence ADAS software development? ISO 26262 makes safety an engineered lifecycle rather than a final test activity. I would begin with hazard analysis and risk assessment, derive safety goals and ASIL classifications, then allocate requirements across hardware and software. Implementation would include diagnostics, watchdogs, plausibility checks, safe states, and freedom from interference. Every requirement needs bidirectional traceability to design, code, tests, and evidence supporting the final safety case. Be sure to mention hazard analysis and risk assessment, ASIL levels, safety goals, technical safety requirements, traceability, freedom from interference, defensive design, verification, and safety case evidence. Question 11. What is the difference between functional safety and SOTIF in ADAS? Functional safety addresses hazards caused by malfunctioning electrical or electronic systems, such as a failed sensor or corrupted output. SOTIF addresses hazards when the system works as designed but its perception or decision capability is insufficient, such as misclassifying an unusual object. ISO 26262 targets faults, while ISO 21448 examines performance limitations and unknown unsafe scenarios. I would use both, combining fault analysis with extensive edge case discovery and validation. In your answer, distinguish failures from performance limitations, explain ISO 26262 versus ISO 21448, discuss unknown unsafe scenarios, intended functionality, triggering conditions, and scenario-based validation. Question 12. How would you structure an ADAS application using a AUTOSAR? I would package perception or control logic as a AUTOSAR software components with clearly defined ports and data types. Runnables would be triggered by timing or data received events through the RTE, while communication, diagnostics, memory, and operating system services remain in basic software. MCAL isolates microcontroller details. This separation supports reuse across vehicle variants, but configuration, timing analysis, and interface versioning must be controlled carefully to avoid integration surprises. Focus on application software, runnables, software components, ports, RTE, basic software, MCAL, communication services, timing events, diagnostic services, and separation between hardware-independent logic and platform configuration. Question 13. How do you design deterministic real-time software for an ADAS ECU? I would start with an end-to-end latency budget for sensing, processing, communication, and actuation. Tasks receive priorities based on deadlines and safety impact, and I would measure worst-case execution time on target hardware rather than trusting average benchmarks. I would avoid unpredictable dynamic allocation in critical paths, control interrupt duration, and protect shared data. Overload handling needs defined degradation, such as lowering processing frequency while preserving essential safety functions. Cover task priorities, deadlines, worst-case execution time, scheduling, memory allocation, interrupt handling, synchronization, processor utilization, latency budgets, overload behavior, and measurement on target hardware. Question 14. What role do CAN and Automotive Ethernet play in ADAS systems? CAN is well suited to deterministic control signals, diagnostics, and robust low-bandwidth communication, while Automotive Ethernet supports high-volume camera, lidar, and centralized compute data. I would use gateways to connect domains and apply appropriate priorities, timing, synchronization, and integrity protection. The design must consider bus load, worst-case latency, dropped frames, and cybersecurity. The correct choice depends on payload size, timing guarantees, architecture, and safety requirements. Mention CAN's reliability and low-cost control messaging, Ethernet's bandwidth and scalability, arbitration, latency, time synchronization, diagnostics, gateways, message integrity, and choosing communication based on data volume and safety needs. Question 15. How would you handle a vehicle cutting into the ego lane during adaptive cruise control? I would detect the cut-in through lateral position, lane boundaries, relative velocity, and track continuity, then reassociate the new lead target quickly. The planner should update collision risk and desired spacing without waiting for several stable frames. Control would apply bounded deceleration and jerk limits, escalating braking if time to collision becomes critical. If lane confidence is poor, I would use conservative occupancy reasoning and clearly transition to a degraded or driver alert state. Discuss rapid target reassociation, lane occupancy, relative velocity, time gap reduction, trajectory prediction, smooth deceleration, collision risk, cutout handling, and robust behavior when markings or detections are uncertain. Question 16. What is your approach to validating an ADAS feature before vehicle deployment? I would validate progressively, requirements and unit tests first, then software in the loop, scenario simulation, hardware in the loop, proving ground trials, and controlled public road testing. Recorded sensor data enables repeatable replay and regression testing, while simulation expands rare and hazardous scenarios. I would track detection, latency, comfort, availability, and safety KPIs by scenario. Release gates should require traceable evidence, defect closure, and explicit approval for known limitations. Be sure to cover requirements-based testing, simulation, replay, software in the loop, hardware in the loop, proving ground tests, public road trials, scenario coverage, regression automation, KPIs, and safety approval gates. Question 17. How would you reduce false positive braking in an AEB system without increasing risk? I would first classify false positives by scenario rather than simply raising the braking threshold. Multi-frame confirmation, trajectory overlap, lane context, and radar camera agreement can reject objects outside the ego path. Hysteresis prevents rapid toggling, while stationary object logic distinguishes harmless roadside items from real hazards. I would evaluate changes against missed detections, especially pedestrians and cyclists, using balanced scenario metrics and near-miss investigations before deployment. Cover multi-frame confirmation, object classification, path prediction, stationary object filtering, sensor fusion, confidence thresholds, contextual cues, hysteresis, near-miss analysis, and preserving sensitivity to vulnerable road users. Question 18. What C++ practices are important when developing embedded ADAS software? I favor clear ownership, RAII, const correctness, strong types, and small testable interfaces. In real-time paths, I avoid uncontrolled allocation, recursion, hidden copies, and exceptions unless the platform explicitly supports them. Smart pointers are useful for ownership outside deterministic loops, but value semantics are often simpler. I would apply MISRA-oriented rules, static analysis, compiler warnings, code reviews, and unit tests while measuring performance on the actual ECU. In your answer, mention RAII, const correctness, strong typing, deterministic memory use, safe interfaces, smart pointers where appropriate, concurrency, static analysis, MISRA C++ guidance, and unit testability. Question 19. How should cybersecurity be considered in an ADAS architecture? I would begin with threat analysis covering sensors, in-vehicle networks, diagnostics, external connectivity, and update channels. Secure boot and signed software protect execution, while authenticated messages, access control, protected diagnostics, and managed keys reduce spoofing and unauthorized changes. Monitoring can detect abnormal traffic, but safety behavior must remain defined if security is compromised. Updates should be secure and recoverable, with cybersecurity activities integrated alongside functional safety engineering. Focus on threat analysis and risk assessment, secure boot, authenticated communication, access control, key management, software updates, intrusion detection, diagnostic security, attack surfaces, and fail-safe responses. Question 20. Describe a systematic way to debug an intermittent ADAS failure reported by a customer. I would first capture exact vehicle state, software versions, environmental conditions, sensor health, and synchronized logs around the event. Then I would replay the data, compare expected and actual outputs, and isolate whether the issue originated in sensing, synchronization, perception, fusion, planning, or actuation. If reproduction is difficult, I would use targeted instrumentation and fault injection. After fixing the root cause, I would add a regression scenario and trace the correction through validation. Make sure to cover reproducibility, synchronized logs, sensor health, environmental conditions, timestamps, software versions, fault injection, data replay, root cause isolation, regression testing, and corrective action traceability. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.